in our first project, we used a linear model, y equals 385x plus 3,129, to make predictions and estimations about the average cost of tuition and fees at U.S. public colleges. Remember this? Based on the number of years after 2000. So trying to determine if there's a relationship between two quantitative variables like year and cost of tuition, so that one of the variables can be used to predict or estimate the other is called regression. Trying to determine the relationship between two variables is called regression. So in today's class, we're going to look at the simplest form of regression called linear regression. Later in the semester, we'll do other kinds of regression. So this table and the corresponding scatter plot tell us about the number of cellular telephone subscriptions in millions in the United States for the period 1993 to 2000. And there's some typos in here. This says 1194. It's supposed to be 1994, and 1995 and 1996. So we have the number of cell phone subscriptions in 1993 was about 19 million. In 2000, it's about 109 million. And we plot the data over here. Based on the overall pattern in the plot, does it look like there's a relationship between those two pieces of information? Yeah, what does the relationship look like? Just describe it. It's going up. Yep. Increasing. As time goes on, the number of subscriptions goes up. How strong does the relationship appear to be? By strong, I mean predictive. Can you use, could you predict how many there are going to be in 2001 based off that picture? You could, yeah. Relatively strong. Yeah, we don't know how far into the future you can predict. I mean, I was in college around this time, and not everyone had a cell phone. It was still like kind of new. So it might actually just get even steeper after this. Yeah. So that might not be a good idea to predict too far into the future using this data. So everybody on your own papers, draw a line through that data that you think visually best fits the data. A line that lies as close to or on the actual data points as possible. Okay, so I'm looking for something like that. Some kind of line that captures the trend of the data, right? The disadvantage of doing this visually, of just sort of trying to capture the trend by visually drawing a line, is that that line is not unique. Every single person in this room drew a slightly different line. Okay? So that is the problem with just sort of doing this like by the looks-it method. So the good news, though, is that we have a statistical method that allows us to determine a unique line, or that's called the least squares regression line, or the line of best fit. It's called the least squares regression line because what we do is we draw a line that makes the sum of the squares. You draw a little square from every data point to the line. You add up the areas of all those squares, and we choose the line that makes the areas of all those squares the smallest. And the specifics of how that's done are not important to us right now. When you take calculus, you'll do a project on how to actually solve that. But for us, we're just going to say, okay, there's some way of getting the best line, and we have technology that knows how to do it. Okay, we don't have to know how to do it. So it turns out that the regression equation that models this data is 12.6236x minus 25,148. Okay, and how we came up with that line, that equation, not important right now. That's just the line that is the best line to model the data. Yeah, that little thing above the Y is a little hat. And Yeah, I know I fixed it on mine, but I had already printed yours. Yeah, that y hat indicates that it's an estimated value. So we have some exact xy values. Like for example, we have 1993, comma 19, right? So we have x, y, and y hat. So when x is 1993, the real y was like 19 point something, and y hat you gain is an estimate from your line, from your equation. So we could come up with y hat by plugging 1993 into this formula, 12.6236 times 1993 minus 25,148. So 10.83 is the estimate from the line. So the actual y and the y hat are pretty different in this case. So we give it a different name so you're not confusing the real y with the estimated y from the equation. And we call it y hat, yep. Okay, so you can describe the overall pattern of a scatter plot by talking about the form. In this case, we're using a line. Although I saw some people drawing curves because a curve might actually be a better fit, right? Some kind of curve like that might be better. But today we're only using lines. That's the only form we're going to use. The direction, meaning is it increasing or decreasing, the line. And the strength, how close are all the points to the line. Okay. We define direction by whether or not the variables have a positive or negative association. Two variables are positively associated if larger values of one tend to occur with larger values of the other. And we say two variables are negatively associated if as one variable gets big, the other variable gets smaller. So look at our scatter plot. Are those variables positively or negatively correlated? Positively, because as the year gets bigger, the number of subscriptions gets bigger also. So we say that's positively associated or positively correlated, same thing. So they are positive. To measure the strength of a linear relationship, you can't rely solely on your eyes. But in general, we measure how close the points are to the line using something called the correlation coefficient. So the strength of the association between two variables reflects how accurately one could predict the value of one variable based on the value of the other. You measure the degree to which two variables are associated with the correlation coefficient, which we call R. It always has a value between +1 and -1. Calculating it by hand is tedious, and we don't really care about the actual computations of how to get it. We just want to know what it means. Technology can give us the number. Okay, so here's how you interpret it. An exact linear fit that's positively associated has an R value of 1. Perfect linear fit where every single data point lies on the line has a correlation coefficient of 1. If you have an exact linear fit, but the association is negative, because as x gets big, y gets small, that has a correlation coefficient of -1. If you have a positive correlation and the points aren't perfect, not exactly on the line, you're going to get some value between 0 and 1, a positive R value between 0 and 1. Negative but not perfect, you're going to get a negative R value between -1 and 0. And like if there's no line, there's no linear pattern to the data at all, we say that the R value is 0. Does what change? Yeah. Like this one, I would say this one might be like 0.9, right? It's not perfect because all the points aren't on the line, but they're really close to the line. So the R value should be close to 1. And this one, same kind of thing. I would say this one might be, it's negative because it's negatively associated. And they're pretty close to the line, like 0.8. And I'm completely just making them up. right? I just know that it's not 1 because it's not perfect, and it's not 0 because there is a relationship. So right now I'm just totally making them up, but your calculator will give you an accurate number. So let's go back and look at our scatter plot. I'm going to erase this. Slope has nothing to do with the R value, except when the slope is positive, the R value is positive, but it's not the same value. When the slope is negative, the R value will be negative. So what do you think the R value is for this graph? It's positive. Is it 1? No, it's a little less than 1. 0.8? Yeah. We're completely guessing right now. We don't have a method for actually calculating this, but maybe 0.8. It's definitely positive. It's not perfectly 1. Let's go a little less. And this is actually not infant mortality. It's cell subscriptions. That was from the previous semester. Yeah. All right, so we know that our calculator can find the line of best fit. It can tell us the equation of the line of best fit, and it can tell us a correlation coefficient. And we can use those things as tools to make estimations and predictions. So now I'm going to go through how to actually do that. So I'll do it on the calculator first, and then I'll show you on Geogebra, and then you're going to do some practice generating regression lines and interpreting. Okay, so on the calculator, I'm not going to go through, I have it all written out step by step for you so you can follow the steps. The Geogebra step-by-step instructions are written on the project, which I'll hand out in just a minute. And as I go through my examples, though, I'm not going to like go through the steps on the paper. I'll just show you. So I'm going to do this example, okay, both on the calculator and in Geogebra. All right, so I've got my calculator. First, I have to input the data. Okay, so to get to the place where you put the data, you use the statistics button, stat, because this is a statistical procedure. So you press the stat button, it's right underneath delete. And then there are 3 menus across the top, edit, calc, and tests. We want to edit because we want to edit the data. So you go into the edit menu and you have lists. List 1, list 2, list 3. This is where we're going to put the data. The X data will go in list 1 and the Y data will go in list 2. So if you want to clear your lists, first thing you do is you put the cursor on the name of the list and you press clear. Don't press delete. It's bad things happen. Just press clear. And it seems like nothing happens, but when you move the cursor back down into the list, it all goes away. Okay, so then why? Okay, so we enter the year data in list 1. So I just type 1993, enter. And if I wanted to, I could measure time not starting at night. We could have 1993 be year 0, but I'm just going to enter it as it is for now. So 1994, 1995, 1996, 1997, 1998, 1999, 2000. All right, so that's all our X data. And then our number of cell phones data, 19. I'm just going to round these to save time. 24, 34, 44, 55, 69, 86, 109. Okay, so one way to do a quick check that you didn't make a typo entering your data, it's not a guarantee, but your list 1 and your list 2 should be the same length, right? It's just one quick thing you can do to check. All right, so we have our data entered. I'm just going to hit quit to get out of here. Second quit. Above the mode button. Okay, I would like to look at a scatter plot of that data. So if you go to y equals, this is where we usually type in things that we want to graph. If there's anything in there, just clear it. And you might have never noticed before now that at the top of this screen, there's plot 1, plot 2, plot 3. That's for plotting data. Okay. So I'm going to highlight plot 1, put the cursor on plot 1 and press enter. So now it's highlighted. That means it's going to plot the data in list 1 and list 2. And to choose a window, I could either look at my data and go to window and pick it based on my data, or I could just press zoom 9 for zoom stat. And there's my data. Looks just like the picture in the notes. And if I'm going too quickly, like I said, these step-by-step directions are all written in the packet, so you can follow them when I let you. Okay, so I now have a scatter plot. Now I want the calculator to give me the line of best fit for this data. So quit, back to the home screen. So you go back into the stat menu, the place we went to put the data in. Go to calc this time, so the second menu over. And option 4, linreg, is linear regression. So you choose option 4. And then in my calculator, in the older versions, you have to type some stuff in here. In the newer versions, they prompt you for some information. So I'm going to do it the old way, and if you can't figure out what it wants, raise your hand and I will come help you. So here I have to tell it what data I'm using, list 1 and list 2, and where to put the result. So list 1, so you can look like right above the number 1 in yellow, it says L1 for list 1. So I hit second L1, and then there's a comma button right above the 7, comma. Then you get to do second L2. So you're telling the calculator, find the best line of best fit for the data in list 1 and list 2. And then you put a comma, and you have to tell it where to put that line, where to put the equation of the line of best fit. And I want it to put it in Y1. I want it to paste the result right here so that I can just hit graph and it will graph. Okay. So I have to put a Y1 right there, and this is really annoying. It's like 3 or 4 steps to get Y1. They're all written out in your notes. But you press the vars button first, stands for variables. You choose Y variables because we want to put it in Y1. You choose function because this is a function, right? And then you get a list of all the Y's, Y1, Y2, and you choose whichever place that you want it to paste. I'm going to put it in Y1. So you need 3 pieces of information. Tell it where your X data is, tell it where the Y data is, and tell it where to put the result. You hit enter, and it gives you the regression equation and the R value. You can ignore R squared for right now. We just want to look at R. If you're missing R and R squared, I believe it's also written in your notes, but I'll walk you through it. There is a button called Catalog, which is second zero. Scroll down until you see, I can't remember what it is. I will see it, know it when I see it. I think it starts with a D. Diagnostic on, that's it. Diagnostic on. Hit enter, enter, and now if you do the regression again, you'll get the R values. You should get your R and R squared. So there's our regression equation. It says it's of the form y equals ax plus b. Then they tell you what a is and they tell you what b is and they give you an R value. And if you go to y equals, it put that equation right in Y1 for you. So it's already pasted there. If you hit graph, it will graph the line. And now if you want to get values, like let's say I want to know what this line predicts for the year 2005, I can go to my table. I could type in 2005, and it will give me the y hat value. All right, so I know I did that quickly, but like I said, you have all of the steps written down step by step with screenshots here in your notes. So when you try it on your own, you can refer to this. And I want to show you quickly how to do this in Geogebra. Okay, so I've got Geogebra open. To enter the data, Geogebra always shows you the algebra view and the graphics view automatically, but it also has a spreadsheet view. So if you go to View, Algebra, Spreadsheet, Graphics, these are all your views. You want to choose Spreadsheet so that you also have a little spreadsheet over here. Okay. In the spreadsheet, I'm going to enter the data. Okay, right? In column A, I'll put the X data. In column B, put the Y data. So column A, I've got 1993, 1995, 1996, 1997. Oh, thank you. Okay, so there's all my X data. And then in my Y data, I'm going to put in the number of cell phone users in that year. And again, I'm going to round them. You probably shouldn't if you're doing like a project or something, but just for the sake of time, I'm rounding these. 19, 24, 34, 44, 55, 69, 86, 109. Okay, so all our data is entered. Then you highlight all the data. So just highlight all the data, right click. If you have a Chromebook, a right click is a 2-finger click. Push down with 2 fingers at the same time. And go to Create List of Points. So right click, Create List of Points. And it has all my points over here and a list of all my points. I can expand this so you can see this is a list of all my points. And why can't I see them in the graphics view if I've created them? I don't need to. They should exist. I have to alter the scale of the graph. Yeah, I got to change the window. So I'm going to hide my spreadsheet view now so it's not taking up room. Just go back to view and hide the spreadsheet. And then I can use my move graphics view to change this. So I can move my axes. I can drag these down to change the scale until I need to be able to see 1993. So I need to see a lot more X because the first X is 1993. There we go. There's all my data. Okay. It looks like it's all in a straight line because I'm just looking at too many X values. Right, so I'm just going to go like this and then spread this out. Changing the scale, you just hover your mouse over the axis until you see a little arrow, little double arrow, and then you click and hold it down and drag. Okay, it might be different in the app. Yeah. So I think if you right click and choose I don't want to just do zoom because that'll change everything.
Oh, I got it. I can change it like manually.
There we go. You can change it. I can change it manually here too. So my smallest X value is 1993. So I'm going to do like 1990. And my biggest one's 2000. I'll do 2005.
How do you get there?
I right clicked on the graph and chose, I can't remember. All right. Okay, so the next thing you're going to do, we've got our data, we've got it plotted, we want GeoGebra to find us the line of best fit. In the input bar, you just type fit line, and then you have to type in the name of the list of points. You hit square bracket, so it kind of tells you how to do it as you write it. So fit line, you're going to do square bracket, and then the name of our list of points is list 1. GeoGebra named it list 1. So you do fit line, square bracket, list 1, enter, and it makes a line and puts its equation up over here. And then to get the correlation coefficient, you type correlation coefficient. So it's this first option here, correlation coefficient. And in the square brackets, you have to put the name of the list of points, list 1. And it says this number B is my correlation coefficient, it's 0.98. Sure.